Hello everyone. Today we'll be going over Chapter 5 of the Glassley textbook, which covers the chemistry of geothermal fluids. Normally, the chemistry of geothermal fluids has little direct impact when used for heating, ventilation, and air conditioning. These geothermal applications only require a temperature of a few tens of degrees centigrade, and meteoric waters that occur in shallow groundwater systems are usually sufficient for these purposes. For higher temperature fluids, which are used in geothermal power production, this is not the case, and the chemistry of geothermal fluids matters. These fluids are often associated with magma bodies or are in regions where igneous activity has occurred in the recent past. In those cases where recent igneous activity is not part of the geological history, high temperature geothermal fluids can form where deep fluid circulation is facilitated by faulting and fracturing, allowing water to reach depth where heat is available to raise the temperature sufficiently to be used for power production. And this is usually around or greater than 120 degrees Celsius. When water temperatures increase to such a degree, the water will interact with the surrounding rocks, taking on chemical characteristics that are influenced by the local geology. These interactions impart a chemical signature to the water. So, geothermal waters exhibit a vast range of chemical compositions, with some dilute and other concentrated dissolved constituents. The geochemistry of these geothermal fluids plays an important role in providing information about the characteristics of a reservoir, including its temperature, mineralogy, and history. The dissolved load can also affect the performance of machinery in a geothermal power plant that's used for heating and cooling and generating power. Other reasons why the geochemistry matters involve reservoir quality evaluation, where their potential economic and environmental impacts are influenced by it. A different yet crucial aspect, which is influenced as well by the geochemistry of natural waters, is the exploration for the resource. Geothermal resources are hard to find since the surface evidence that a high temperature resource is present at depth may not be so obvious. Most of the time, these resources are detectable through chemical signatures in surface waters. Some of these signatures can be specific chemical constituents that indicate the presence of a heat anomaly at depth. In other cases, it may be shifts in the distribution patterns of certain elements, isotopes, or compounds, or changes in ratios of elements. As you can see in table 5.1 from the textbook provides a list of common aqueous species found in geothermal waters along with their atomic and molecular weight and ionic radii. There are cations such as H+, and metal ions such as lithium, sodium, and potassium. We also have anions like chloride, bromide, and fluoride ions. And there are compounds such as hydrogen sulfide. This is a safety hazard because of its toxicity to animals, including humans. Effective means effective means have been and are still being developed to handle the scaling, corrosion, and environmental problems caused by dissolved constituents in geothermal fluids. Water, similar to any other chemical compound, reacts with materials with which it comes in contact. An example of this would be the exchange of atoms via diffusional processes at the interface of solids making contact with each other. These interactions, however, are of limited extent and are slow to occur. Liquids, which the constituent molecules are highly mobile, will relatively quickly interact with whatever compounds they are in contact. In the case of water, the reactivity is significant. This is a reflection of the fact that water molecules are polar, meaning they possess electrical polarity due to the orientation of the hydrogen atoms covalently bound to the central oxygen atom of a water molecule. Compounds such as minerals, which invariably have exposed atoms and their associated electrical charges on their surface, will interact with water because of its electrically polarized nature. As a result, water is an excellent solvent, meaning it has the ability to dissolve constituents or solutes and carry them as a dissolved load. This charge polarity also leads to the water molecules linking together to form a weak polymeric structure. The water molecules will tend to orient themselves such that the side of a water molecule that has the net positive charge will be in proximity to the net negative charge portion of adjacent water molecules. This structure linking changes in a short period of time, with water molecules aligning with different neighbors very quickly. This property has a strong influence on the way in which the internal energy of a volume of water changes with temperature. At low temperatures, the vibration rate is relatively low, and the length of lifetime of the polymeric chain is relatively long. As temperatures increase, vibration rate increases, and the length and lifetime of the polymeric chains decrease. Many solutes are themselves charged, in which case they are called ions. Positive charged ions are called cations, and negatively charged ions are called anions. Because it is a matter of universal human experience that water is not electrically charged, it's clear that the dissolved load is exactly electrically balanced. In other words, the positive electrical charge of the total dissolved load of cations exactly neutralizes the negative electrical charge of the total dissolved anions. Any collection of compounds is composed of chemical constituents, whether they're metals, mixed gases, or liquids. The minimum number of these chemical constituents that are needed to fully describe the collection of substances in a system is defined as the components of the system. How these components are identified depends on the way we define the system and how it's to be analyzed. In developing our list of components, it's important that they describe the system completely. They are not themselves composed of two or more entities that occur in our system. The entities that make up the system are the phases, which can be minerals, gases, or liquids. An example of this would be the minerals quartz, tridymite, and chalcedony, all which have the same chemical formula of silicon dioxide, SiO2. These three phases are the system we will consider. The difference between them is how the atoms in the mineral structures are arranged, similar to carbon, diamond, and graphite. This leads to differences in appearance and properties, as you can see in the images. There are two ways in which the components of this system can be defined. One way is to note that the elements silicon and oxygen compose of all the minerals in this system and can therefore completely describe the chemical properties. In this case, the system would be treated as a two-component system. It's also possible to use silicon dioxide as the chemical component because it too provides a complete description of this system, as all these rocks are or minerals are silicon dioxide. This depends on our interests in the system and what behaviors we wish to understand. If our interest is in understanding the behavior of the minerals in the system and not the elements or isotopes of the system, using silicon dioxide as the chemical component is perfectly good and preferable and necessary way to describe the system because it allows the smallest number of components to be used for defining the system. If, however, We were interested in the dissociation of the minerals into their respective atomic constituents, or wanted to understand isotopic behavior, then we would have to use silicon and oxygen as the components rather than silicon dioxide, since that would not be sufficient. Each chemical component in a mineral has a chemical potential μ, which has the units of joules per mole. Chemical potentials are analogous to gravitational potentials or electrical potentials. They are a measure of the tendency of a chemical component to change from one energy state to another. For a mineral, the state would correspond to a specific way in which the atoms in the structure are arranged. Let's consider the transition from one phase to another, where quartz transforms to tridymite. If all pressure and temperature conditions at which this reaction occurs are taken into account, a boundary pressure temperature space will be defined. On one side of which quartz, the reactant, will be stable, and on the other side the product will also be stable. Along the boundary, the chemical potential of silicon dioxide in both phases for quartz and tridymite are both equal. The various reactions that are possible in the example system are easily represented as expressions between components because there's only one component in the system and that component's the only one present in the phases we were considering. In reality, geothermal systems are more complex, and keeping track of how all the components are individually changing as the physical conditions evolve is simply too cumbersome. We use this relationship to account for these changes instead, where the Gibbs energy function of phase J is equal to the sum of the chemical potentials of components I in phase J. In the summation, it is convention that the products are taken as positive and the reactants are taken as negative. The way in which the chemical potentials of components change in responses to change in pressure and temperature or other state variables is represented by activity or alpha. Activity is a thermodynamic measure of the difference between the chemical potential of a component in a phase from one set of conditions to another. The change in chemical potential follows the form, where the first term, mu raised to Tpx, is the chemical potential of the component I at some pressure, temperature, and composition x of the phase being considered. Mu node is the chemical potential of component I at some standard state, including a reference composition. This relationship allows us to determine the chemical state of a system from the chemical composition of the phases in the system. They also provide a means to predict the behavior of a system if it is subjected to conditions that are different from those that determine its current properties. Opposingly, for considerations regarding geothermal systems, the chemical composition of phases in a system contains information about the temperature and pressure the system has experienced. So let's consider an example where we have a pot of boiling water where once the pot is boiling, we immediately remove it from the stove and place it in a perfectly insulated container. Just before we close the container and perfectly isolate it, we pour in exactly 10 grams each of table salt and quartz sand, and quartz sand is silicon dioxide, both of which we've ground to a particle size in which every particle has a diameter of, let's say, exactly 10 microns. What would we find if we opened the container 10 minutes later? And how about an hour later? Would it be any different if it was a year later? So, if we judge from experience, we can say that the table salt probably dissolves relatively quickly and eventually completely disappearing. But would it be gone after 10 minutes? And if we kept adding 10 grams of salt, how much salt could we add before to the 100 degrees water before no more would dissolve? So we can answer these questions by using the law of mass action and reaction rate laws. The law of mass action relates to the chemical reactions that have achieved equilibrium. So let's take for example the dissolution of halite, or the salt basically, which can be written as a chemical reaction in which the halite in the reactant and the ions in solution are the products. Take into account that electrical neutrality is perfectly maintained when halite is dissolved. This is true for all complete reactions as charge is conserved. As the halide dissolves in the water, the overall reaction proceeds from left to right. If we could see the individual salt crystals at an atomic scale, we would observe that as the atoms on the crystal faces separate from the crystal structure, enter the solution as ions as dissolution occurs. But we would also see a few ions in the solution reattach themselves to the crystal face as precipitation occurs. So we have two conflicting reactions going both ways, but overall the net effect is that the rate at which atoms are removed from the crystal and enter the water as ions is much faster than the rate which they reattach to the crystal, which results in dissolution. The equilibrium point is achieved when the reaction is proceeding in both directions at exactly the same rate, resulting in no change in the amount of solid halite or the number of ions in solution. In this state, the solution would be saturated in halite. The law of mass action states that at any given set of conditions, the following equation will hold true, where alpha is the activity and K is the equilibrium constant, which is a function of temperature, pressure, and composition of the solution. This is figure 5.2 from the textbook, where the variation of the log of the equilibrium constant K for the halide dissolution reaction and the quartz dissolution reaction is shown as a function of the temperature up to 300 degrees Celsius. Um, the activity of solid minerals that are pure is equal to 1. For dissolved species, intuition would suggest that the activity would be equal to the molality of the species in solution. As a result, the equilibrium constant would change linearly as temperature changed. But however, as we can see from the curvature of the line defining the measured values for the log of the equilibrium constant K for a halite in figure 5.2, we can determine that there's a more complex process affecting the behavior of the ions in solution, as it's not linear. This non-ideal behavior is due to the interaction of the charged ions in solution with each other and the polar water molecules. Because sodium and chlorine ions have different ionic radii, they'll also have different charge densities, different frequencies with which they vibrate in the solution, and different number and orientation of water molecules that would be loosely bound to them by electrical charge interactions. In addition, by adding to by adding water ions to water by adding ions to water, it modifies the polymeric structure of water, which in turn affects the internal energy of the solution. Together, these effects combine in nonlinear ways to influence how changes in the dissolved concentration of solutions in solutes in water affect the internal energy of a solution. It's this behavior that is considered non-ideal and has led to the concept of activity coefficients. An activity coefficient can be defined as a factor which, when multiplied by a species molality, corrects the measured concentration in a solution so that the mass action law for a given reaction is satisfied. For the halide reaction, this means the mass action expression takes this form, where gamma I is the activity coefficient for species I. For dilute solutions, the activity coefficient is close to 1, and for most purposes, the measured molal concentrations can be used in calculations. Dilute solutions are those that have total dissolved solute loads equal to or less than that of seawater, which has a dissolved load of about 35 parts per thousand. For more concentrated solutions, the effect of non-ideality can be significant, and we need to take that into account. Establishing whether a chemical reaction, such as halide dissolution reaction, will actually take place is accomplished by comparing the composition of the solution to the value of the equilibrium constant using the following expression, where A is called the affinity in joules per mole, R is the universal gas constant with a value of 8.314 joules per mole Kelvin, T is the temperature in Kelvin, and Q is the activity quotient for relevant species in the applicable reaction. K is also the equilibrium constant for the same reaction. If the measured solution composition results in an activity product that is equal to K, the affinity will be 0, indicating that the solution is in equilibrium with the solids, and no net dissolution or precipitation will occur. If the affinity were greater than 0, the concentration of the solutes exceeds the equilibrium value, and the solution would begin to precipitate solid. This situation is one in which the solution is supersaturated in the solid involved in the reaction. For affinities less than 0, the reactant, or in this case the solid phase, which continue to dissolve until it is completely dissolved or the activity product of the solutes becomes equal to K, and equilibrium would be achieved. This situation with respect to the values of affinity suggests that mathematically A must be equivalent to the Gibbs energy function of a reaction as indicating the following equation, where affinity is equal to the Gibbs energy of the products minus the Gibbs energy of the reactants, which is also equal to the enthalpy of the products minus the enthalpy of reactants subtracted by the product of the temperature and the entropy of the products minus the entropy of the reactants. This relationship leads to the fundamental expression delta G equals minus RT ln K, which is a statement of the relationship between the activities of the species involved in a reaction and the conditions under which they will coexist in thermodynamic equilibrium. So, going back to the question of adding 10 grams of salt and quartz into the pot of boiling water, we can finally answer that question with reference to figure 5.2. At 100 degrees Celsius, the value of log K for the halide dissolution reaction is about 1.6 on a molar basis, and assuming ideal behavior of the ions in solution, this means that a little more than 6 moles each of sodium cations and chlorine anions must be dissolved in solution to achieve saturation. We know that the molecular weight of sodium is about 22.99 grams per mole, and chlorine has a molecular weight of 35.39 grams per mole. So the respective masses of sodium and chlorine in saturation solution will be a little more than 145 grams and 220 grams. So clearly, the 10 grams of added salt would dissolve completely, and the solution would be far from its saturation point. The resulting affinity and Gibbs energy would be much less than zero. Now, on the other hand, with the 10 grams of quartz added, we can see that the K value at 100 degrees Celsius for quartz is about 0.001. This translates to a total aqueous silicon dioxide concentration of about 0.06 grams at equilibrium, or approximately 60 parts per million. Clearly, in this case, we've added way too much quartz than would ever dissolve. As a matter of fact, so little would dissolve that it wouldn't be noticeable unless we carefully weighed it before and after our experiment. In other words, quartz has a low solubility under these conditions. Solubility is the combination of all the processes we've discussed so far in this lecture. Solubility is the maximum concentration of a solute in a solvent that can be maintained at a given temperature and pressure. It is measured in units of mass per volume or mass per mass. Common units are parts per million (ppm) by weight, and moles of solute per kilogram of solvent, or molality. So, in the example of the salt and quartz, um, both exhibit changes in solubility as temperature increases, but the pattern is different. Halite solubility increases until about 65 degrees Celsius, at which point solubility begins to decrease slightly over the temperature range to 300 degrees Celsius. However, um, quartz solubility, however, increases throughout that range, and although it drops precipitously beyond about 350 degrees Celsius. Part of this difference in behavior is a reflection of the nature of these reactions. The halite and quartz reactions are representative of dissolution and precipitation reactions that will occur in geothermal systems. The process of quartz dissolution involves a neutral molecule detaching from mineral structure and entering the solution as neutral aqueous species, in this case aqueous silicon dioxide. The interaction of the electrically neutral component with the polar water molecules is one which the aqueous species is surrounded by water molecules in a coordinate structure in which the number of water molecules surrounding aqueous silicon dioxide is a function primarily of temperature. But for the halite, as for the case of halite, dissolution occurs by individual ions on the surface of the crystal lattice breaking to ionic bonds, which binds them to the structure and entering the solution as charged anions and cations. Because of their electrical charge, they interact more strongly with individual water molecules than the neutral silicon dioxide species in solution. This leads to more complex behavior in solution because any other charged solute components will also be interacting with the water molecules. As a result, solubility of halite in water can be strongly influenced by other solute components. A third type of solubility behavior can be demonstrated by considering the dissociation and precipitation of the mineral calcite. Calcite is calcium carbonate, CaCO3. The dissolution of calcite results in a calcium cation and carbonate anion. This reaction is coupled to the hydrolysis of the carbonate ion to form bicarbonate. This carbonate bicarbonate equilibrium is obviously affected by the activity of the hydrogen ion in solution, which is also the determinant of the acidity of the solution, as we'll discuss later. It is through this mechanism that pH becomes an important control on carbonate dissolution and precipitation. The calcite dissolution exhibits an important characteristic that certain salts express when they dissolve, namely retrograde solubility, which is defined as decreasing solubility with increasing temperature. Other carbonate species, such as dolomite, as well as sulfate species such as anhydrite, show similar retrograde solubility relationships with temperature. Figure 5.3 compares the solubility of quartz and calcite as a function of temperature and, in the case of calcite, also as a function of the concentration of other solutes in solution. The retrograde solubility for calcite is obvious. The calcite solubility is also sensitive to other components in solution as well. At 150 degrees Celsius, for example, calcite solubility can differ by more than 300%, depending on the solution composition. These examples demonstrate an important aspect of how fluid chemistry may evolve along a flow path. For example, let's assume a geothermal fluid is at 250 degrees Celsius and is migrating to a cooler region where the temperature is 100 degrees Celsius. Let's also assume that the fluid is pure water saturated with calcite and quartz. And this means the solution will begin with a silica solubility of about 6.6 millimolar and a calcite solubility of less than 0.5 millimolar. As the fluid migrates and cools, quartz will be precipitated because its solubility will decrease, but the solution will become richer in calcite components. If calcite is in the rock the water is migrating through, because the calcite solubility increases with decreasing temperature. By the time the solution has equilibrated over the 100 degrees Celsius environment, it finds itself in the solubility of quartz, um, finds itself in. The solubility of quartz will have dropped to 1 millimolar, whereas that of calcite will be nearly 6 millimolar. The halite quartz and calcite dissolution and precipitation reaction indicate that the types of mechanisms that affect how fluids migrating through a porous or fractured medium will react with the rock framework. If the fluid is undersaturated with respect to the minerals in the rock, it will dissolve the minerals and thus increase the porosity and permeability along its flow path. If the fluid happens to become supersaturated with respect to one or more minerals, it will precipitate those minerals and decrease the porosity and permeability. Another important reaction process that has minimal impact on porosity and permeability evolution, but which has important implications for assessing geothermal systems, is ion exchange. Although some minerals, such as quartz, have a fixed chemical composition of silicon dioxide, other minerals can accommodate a variety of ions in their structure. An example of this is alkali feldspar, which is one of the most common minerals in the Earth's crust. There are two main end members for end member chemical formulae for alkali feldspar, which are sodium and potassium feldspar. These two pure end member compositions are occasionally found in nature, but more commonly the mineral is found to be a mixture of the two end member molecules. The relationship between the end members can be written as the exchange reaction with potassium and sodium ion, with a potassium and sodium ion. In figure 5.4, the log of the equilibrium constant for the exchange reaction is plotted as a function of temperature. The large variability of log K over a relatively small temperature interval raises an important point. An aqueous solution in contact with the equilibrium with alkali feldspar at a given temperature should have a specific sodium ion to potassium ion ratio. In other words, the ratio of Na plus to K plus in a solution is temperature sensitive and has the potential to act as a geothermometer. Although the chemical processes we've discussed provide a means for evaluating the dissolution and precipitation controls on minerals for a given set of conditions, and how those reaction processes will influence fluid and mineral compositions, they don't tell us anything about the rate of these processes to evaluate how quickly or even whether equilibrium will be achieved. And to know how fast these dissolution or precipitation reactions will occur, we have to consider reaction kinetics. How quickly materials dissolve in or precipitate from a solution, and therefore how quickly equilibrium will be approached, is determined by the temperature and pressure, the effective surface area exposed to the solution, the chemical composition of the solution, and how readily mineral components can be removed from or added to the exposed surface of solids which the fluid is in contact with. The rate at which such a process proceeds is called the kinetics of the reaction. Experimental studies over the years have shown that mineral dissolution can be described by equations using the variables we've discussed so far. There has been a number of proposed reaction rate laws, many of which work quite well for specific types of minerals from which they were derived, but often cannot be successfully applied to other families of minerals that are vastly different, which have, in terms of structure or chemistries, from the reference mineral system. This is why we have to be careful when applying rate laws when we're attempting to understand the time-dependent evolution of natural geological systems. To quantitatively capture the overall behavior of a reacting system, the functional relationship must take into account how reaction kinetics are affected by various parameters. We can accomplish this by noting that each variable has an influence on the Gibbs energy function of a reaction. At equilibrium, by definition, the value of the Gibbs function is 0. However, far from equilibrium, the reaction rate large is a large positive or negative number, and we can see this relationship in figure 5.5. This is a general reaction rate equation written in a form that uses the measured dissolution rate for reference, where R is the rate in moles per second. S sub A is the effective surface area exposed to the fluid in centimeters squared. K is the far from equilibrium rate constant in moles per centimeter square seconds. T sub FAC is the temperature correction factor for the rate constant K, and this is usually an Arrhenius function. Alpha is a power function that accounts for a change in the rate close to equilibrium conditions, and phi is a function that modifies the rate for precipitation relative to that for dissolution. AI Alpha I accounts for the dependence of the rate on the activities of specific components in the solution, and often this mainly is a reflection of the activity of the hydrogen ion H+, and omega is the power dependence that accounts for the particular dissolution of precipitation mechanism. Given the number of moles present, the time required to dissolve material or time required to precipitate a given amount of material can be calculated from this equation, but this is rarely the case since there's usually insufficient data to do so. Geothermal fluids always contain a dissolved gas component that can play an important role in establishing the chemical characteristics of the fluid, as well as providing insights into the properties of the geothermal reservoir. The source of and influence of that component are multifaceted. When magmas are generated, usually many kilometers underground, they include components of the rocks that melted to form them. Because the melting process involves large volumes of many different minerals, the melts that are generated are complex chemical systems that contain virtually every element in the periodic table. As the melts migrate to shallow levels in the crust, and they cool and start to crystallize, a fractionation process occurs in which some elements are preferentially incorporated into the newly forming minerals, and others are excluded because they do not fit into the crystal structure of the new minerals. Many of the excluded elements and compounds have a tendency to form volatile compounds, including water vapor, carbon dioxide, hydrogen sulfide, oxygen, methane, and chlorine. As the magma crystallizes, the diminishing volume of molten material that contains these compounds as a dissolved load eventually reaches saturation in them and they begin to exsolve, migrating as gases and fluids from the crystallizing magma into the surrounding rock. As these volatiles migrate upward, they interact with the um, geothermal fluids and groundwater. Consequently, geothermal fluids can contain elevated concentrations of these constituents. The host rocks through which heated geothermal fluids migrate also can contribute to the development of a dissolved gas component. An example of this would be if the rocks contain calcite, dissolution of the mineral will increase the amount of carbonate and bicarbonate, which ultimately will increase the dissolved carbon dioxide. Here we have figure 5.7, which shows the relationship between chloride content in milligrams per kg in geothermal fluids and the pH of the solution for the geothermal waters. The gases and the dissociation of the ions leads to the production of hydrogen ions, which influences the acidity of the solution. The very strong correlation between acidity and chloride concentration reflects the fact that the addition of chloride to a solution will make hydrochloric acid, HCl, and hydrochloric acid strongly favors high activities of hydrogen ions in solution. We can see that from the figure that the geothermal fluids in New Zealand have relatively low chloride concentrations, and they're actually basic rather than acidic. Mexico and the Philippines have almost neutral pH values, with the Philippines having neutral, and they also have approximately 10 times the chloride concentration than New Zealand. Iceland has a pH around 6.4, and the Salton Sea, California has a much lower pH of 5.1 approximately. In geothermal systems used for power production, the dissolved gases can have an important impact on the engineering and management of the power generation complex. Dissolved gases will stay in solution unless the pressure is decreased, which is exactly what happens as geothermal fluids are brought to the surface and used to turn turbines. Once steam forms, a new process begins to influence the behavior of the dissolved gases, namely the necessity to partition the total mass of each dissolved species between liquid and gas, which is steam. Thermodynamically, this partitioning process reflects the driving force for all substances to achieve a thermodynamic equilibrium condition. We rely on experimental data to establish the partitioning relationship for any species because the theoretical quantum mechanical calculations are challenging and tedious. The following function for describing partitioning behavior the following is a function for describing the partitioning behavior, and it's quite an intimidating function, but knowing the factors which influence the steam liquid distribution coefficient Kd is useful. First term, Kd, is the mass ratio between the gas and liquid phase of a species of interest. T is the temperature in Kelvin. T sub Cp is the temperature of the critical point of water, and that's equal to 647 point almost 1 Kelvin. Rho I is the density of water at the temperature of interest, and rho Cp is the density at the critical point of water. And E, F, G, and H are correlation parameters that are derived from fits to the experimental data, um, which are displayed in table 5.4 of the textbook. So let's go over a case study of a silica system. We've talked a lot about quartz in this lecture, and it's ubiquitous in geological systems. The properties of this system provide an example of the range of issues and their complexity that must be borne in mind when working with geological systems that make up geothermal sites. As we said, the chemical composition of silica is silicon dioxide. However, silicon dioxide occurs in several different forms or polymorphs. The minerals alpha cristobalite, beta cristobalite, alpha quartz, and beta quartz, and tridymite are some of the minerals forms that can occur in geothermal systems. As we've gone over before, the difference between them are in how the individual atoms that form the crystal lattice for each mineral are arranged. Opal, as an example, is a form of alpha cristobalite that contains water in microscopic pores and is also relatively common. As well, amorphous silica, which is a form of SiO2, as glass-like with no crystalline structure on the scale of microns or larger, can also occur in a variety of settings where rapid precipitation occurs. Each polymorph has specific conditions within which it is stable. So under dry conditions, alpha quartz is stable from surface conditions up to 573 degrees Celsius, and at that temperature, it transforms to beta quartz, and above 867 degrees Celsius, tridymite is the stable polymorph of silicon dioxide. In the presence of or water vapor, silicon dioxide can take forms as alpha cristobalite up to 220 degrees Celsius, beyond which beta cristobalite forms, and this transformation is reversible in the presence of water vapor. Um, the different pressure temperature fields reflect the different thermodynamic properties for the various polymorphs. By implication, therefore, each polymorph must also have its own rate constant for dissolution and precipitation, and its own saturation value as a function of temperature. Here in figure 5.10, we have the saturation values for amorphous silica, alpha and beta cristobalite, and quartz as a function of temperature. At temperatures below 100 degrees Celsius, All of the waters are supersaturated with respect to all the polymorphs shown in the figure. As a result, geothermal generating equipment that is in contact with geothermal fluids has the potential to acquire deposits of silica, which is known as silica scaling. And this is a problem geothermal power facilities have to remediate using different processes to prevent silica scaling. Um, the rate at which silica precipitation occurs is not really predictable, despite the work that has been done to evaluate silica polymorph precipitation and dissolution kinetics. Um, it has been shown that the precipitation rate of amorphous silica in New Zealand geothermal systems is influenced by the concentration of aluminum solution as well as other things. This and other chemical properties of solution can be a factor influencing reaction rates and argues for the importance of acquiring high quality chemical analysis for geothermal fluids in order to fully understand the property of any specific geothermal site. So let's try an example question. If you have the equilibrium constant for a reaction uh, and it was equal to 3.7, what would be the Gibbs energy of the reaction at 300 degrees Celsius? Um, so we're given the equilibrium constant, which is 3.7, and the temperature is 300 degrees Celsius. We convert that to Kelvin, adding 273, and we get 573 Kelvin. To find the Gibbs energy of reaction, we can use the following equation. Delta G equals minus RT ln K. Plugging the values in, we can get a Gibbs energy of reaction equal to minus 6,233 joules per mole.